Okay, I'd like to start. So today's class is about this beta parameter and how it affects the ability of the network to store memories. Now, there are two the fact that we're dealing with this beta is important for two reasons. One is biological, and true real neurons are not binary, so it is important to understand what are the implications of considering neurons that are not binary. However, there is perhaps a more interesting reason, and the reason is that it turns out that when considering the binary neurons, indeed, we were able to show that we're able to show that desired memory patterns under certain conditions are indeed fixed points of the dynamics. However, it turns out that there are many more fixed points which are not the desired fixed points. And this will become apparent when considering the case of beta, and nonlinearity that is less strong than sign nonlinearity can eliminate many of these solutions or many of these fixed points which can be considered as fixed points that perhaps are detrimental to memory retrieval. And this will become apparent later today. So the dynamic equations that we consider are Ri dot is equal to minus Ri plus hyperbolic tangent of sum over j, jij, rj, and as before, ji not equal to j is equal to 1 over n, sum over mu, pi mu, pj mu, and pi mu, pj mu are plus minus 1 with a probability 1/2. And we defined something that we called an overlap parameter. We defined it as mu, which is equal to 1 over n, sum over I, pi mu Ri. This is a measure of how similar the activity of the network is to memory pattern mu. And what we did last week, let's write it here, ji not equal to j is equal to 1 over n, sum over mu, pi mu, pj mu. Can delete this. And we started by considering the case of a single memory pattern, p is equal to 1. And it turns out, and this we did last week, is that the dynamic equation for M1 is M1 dot is equal to minus M1 plus hyperbolic tangent of beta M1. And then we asked ourselves, what's the fixed point of this equation? Well, the fixed point of this equation, M1 star, is equal to hyperbolic tangent of beta M1 star. And I think this is more or less where we where we stopped last week, right? Questions so far? And then I asked you, what kind of solutions does this equation have? And how do these solutions depend on the value of beta? Now this is reminiscent of what we did, something that we did very early in this course when we considered what? We did something very similar in the I'm sorry? The OTAPs, right. So the OTAPs and later the all-to-all connectivity resulted in equation that had a similar form, but at that time we used the general function g rather than considering this particular function, the hyperbolic tangent. But the results, so what were the results? Long time ago when we spoke about the OTAPs. Right, so there was a bifurcation. And what did it depend on, this bifurcation? Well, here it will depend on beta, but what generally there was a regime in which there was one solution, a regime in which there were three solutions, two stable and one unstable. And the stronger the nonlinearity of G was, or going from G that was shallow to G that was very nonlinear, we moved from one solution to three solutions. So we expect something similar to happen here. And in fact, this is what we get. So let's consider the case of, so how are we going to study the solutions of this equation? Well, as before, the way to do it would be to plot m as a function, to plot hyperbolic tangent of beta m as a function of m, and then to plot m as a function of m. So this would be m as a function of m. So m as a function of m is just the identity. And then hyperbolic tangent of beta m as a function of m, well, this would depend on the value of beta. So if beta is very large, how would the hyperbolic tangent look like? It would be close to a step function, going from -1 to +1. So let's say that this is -1, and this would be +1. So if beta is very large, then tangent hyperbolic of beta m will look something like this. And indeed, we have these three fixed points that we studied last time. There would be two fixed points that we expect, and we will prove it in a sec. We expect them to be stable, and there would be one unstable fixed point near the origin. And so this would correspond to beta that is very large. And what happens to beta that is very small? How will it look like? So the function itself will look something like this. Eventually, it will saturate at plus and -1, but it will not cross the line m is equal to 1 in more than 1 point. So we'll have one stable fixed point here. So this would be beta that is very small. Okay, so we more or less understand how the solutions of this equation. The question now is what would be the value of beta such that the dynamics will go from one solution to three solutions, or the bifurcation point. How do we find the bifurcation point here? So what's the value of beta such that we change from one solution to three solutions? So to save time, any ideas? I'm sorry? No, I said very much larger or much smaller than 1. I mean, it could be 2 or 1 over pi, and this would still be true. So we understand we understand the behavior in two extreme cases. One that it's very large and one that's very small. It turns out that indeed the transition, the bifurcation point is at 1. But the question is, how are we going to prove it? Yes?
What we're trying to get here is an M, to get this bifurcation, to get it actual a map between the activity of the network and the memory itself. So after we get the bifurcation, we can get the negative, also the negative memory patterns, right? Because it comes with the plus 1 and the minus 1.
This is now the first, feel free to ask questions in Hebrew. I'll translate if necessary. So, going to your question, there are two issues here. Okay, one is the mathematical issue. I have this equation, I want to solve it. I don't care about the interpretation. Another issue is the issue of interpretation, and especially with respect to memory patterns. So, if I understand you correctly, you are now sadly concerned that if we'll have a solution that is non-zero, positive solution, we'll also have a negative solution. Now this is indeed the case, and actually if you'll go back to the case of the case of beta is infinite, you'll find that the negative of the memory patterns are also memory patterns. And this you can see in this plot when at the bifurcation point we indeed we have two fixed ones, one in the positive regime, one in the negative regime, and we can discuss so we can discuss the interpretation. I mean, does it make any sense, or is it not? Is it a bug of this model, or is it a feature of the model? But this is for a later discussion. Now I'm asking a mathematical question. How do we know that the transition from 1 to 2 is from 1 to 3 fixed points occurs at beta being equal to 1? Yes? Okay. Okay. Okay, so one way of finding or addressing this question is exactly to look at the slope of this function at the fixed point, at the 0 fixed point. So, if we write g of x is equal to hyperbolic tangent of beta x, then the derivative g prime of x is equal to 1 minus hyperbolic tangent of x beta x. Sorry. Well, it's easy to prove that this is the derivative, and this fixed point is looking at the 0 fixed point. So g prime of x, the point x is equal to 0, will be equal to beta. So when beta is larger than 1, then the slope of this function is larger than 1. So it has to go this way, and since it saturates, eventually it will cross this line. If beta is smaller than 1, then this slope will always be smaller than this slope, and we'll have only one fixed point, and we can plot something like this would be m star as a function of beta, and as long as beta is smaller than 1, then we have a single fixed point, and when beta is larger than 1, then we have a bifurcation, with two solutions, and the limit of beta going to infinity, this would be 1 and -1. So this is a behavior of the model. So one thing that we can learn, well, several things we can learn about the idea of a memory in this framework. So if beta is smaller than 1, then even in the case, remember, we are talking about the case of a single memory pattern, we can't even maintain a single memory pattern. If beta is larger than 1, then we will be able to maintain a memory pattern. However, its value will not be, the overlap will not be 1. The overlap will depend on beta. The larger beta is, the larger will be the overlap. Another thing that we can do in this case is what? Something that we have been ignoring in the last weeks. Stability. So we can consider the stability. So how are we going to do that? So we will linearize this equation around the fixed point. So we'll have so how are we going to do that? Sorry? Yeah, okay. So delta M1 dot is equal to minus delta M1. So we are linearizing around the 0 fixed point. Plus what? Well, we've already computed the derivative. So this would be plus beta delta M1, or delta M1 dot is equal to minus 1 minus beta delta M1. So again, when beta is smaller than 1, then the fixed point is stable. When beta is larger than 1, then this fixed point is stable. What about these fixed points? They will be stable because the slope is smaller than the slope of 1. There is a delicate issue here, though, I'd like to draw your attention to. How many equations do we have here? N equations. So when computing stability, how many equations do we need to, or what kind of how are we going to compute stability? In fact, we need to compute stability on this, not on this. This is a single equation. And here we have n equations. So there's something not exactly kosher going from this to this. Yes.
לא הבנו את עצמנו, אם אחת מהן היא לא יציבה, אז כולם לא יהיו יציבות במקרה הזה.
So the comment is, well, actually we did something that is wrong, because we considered stability only in one direction. It's possible that the network will be unstable in other directions, right? That's your concern. And then this stability analysis is in fact not very informative. In fact, we found only one direction in which it is stable. There are n-1 directions in which we are unsure about what's going on. So how are we going to address this puzzle? So the solution would be the following. So P1 is one memory pattern, and M1 is the overlap of the pattern of activity or the projection. We can think about this M1 as a projection of this pattern of activity on this direction. Right? So M1 is a projection of this n vector, this pattern of activity of the entire network, on the projection on one direction. In order to study the stability, we need to project the pattern of activity of the network on all other directions, on all other n-1 directions. Now, if we do that, so we can define M2, M3, and M4 on, well, patterns that are orthogonal to P1. And then we will have terms, when we talk about sum over J of Ji, Rj, these will be terms of the projection of P of another direction, let's call it P2, on R1. Now, if M1 has a positive projection, well, in general, these projections will be equal to 0. So in general, in all other terms, we will just have an equation that will look like M2 is equal to minus M2. So for this reason, this analysis is kosher, because it's very easy to see that in all other n-1 directions, the dynamics are stable. Let's do an example, or let's repeat this analysis, this time when P is equal to 3. Okay, let's do another example. So P is equal to 3, and Jij is equal to 1 over n, sum over mu, Pi mu, Pj mu. Okay, the input to neuron I is equal to sum over J, Jij, Rj, which is equal to sum over mu, Pi mu, 1 over n, sum over J, Pj mu, Rj, which is equal to sum over mu, Pi mu, m mu. So the input to a neuron can be written as a sum over all memory patterns, in this case 3, pi mu times the overlap with that memory pattern. And now we can write, as before, we can consider the dynamics of each of the overlap parameters. So m1 dot would be equal to minus m1, as before, plus 1 over n sum over I pi1 hyperbolic tangent of beta sum over mu pi mu mu. This is just 1 over n sum over I pi1 times r. The minus ri will give us the minus m1, and this is the contribution. This is hyperbolic tangent of the input to neuron I, and this is sum over all neurons weighted by pi1. We have 3 such equations, one for M1, one for M2, one for M3. So previously it was easier because we had M1 as a function of M1, and that's it. But here we have pi1, and we have a sum over pi. So how are we going to address it? What can we say about this term? So this term is composed of n variables. Right? But in fact, these n different variables, n different stochastic variables, can attain a finite number of values. Right? Because pi1, we have pi1, pi2, and pi3, and each one of them can be either +1 or -1. So at best, or maybe I should say at worst, we have 8 different values. And these 8 different values will be equally distributed. Each one will appear with a probability 1 over 8. And since we are summing over a large number of variables, we are averaging over a large number of variables, then we expect that this term will be approximately equal to its average over the realization of memory patterns, plus corrections. And these corrections will be of order 1 over square root of n. So in fact, what we can do, we can replace this term by its average. So M1 dot is equal to minus M1 plus average, and this is how we denote average over realizations, of the product of P1, which can be plus or minus 1, times hyperbolic tangent of sum over mu, mu going from 1 to 3, of P mu mu. So what we are doing now, we are taking this term and replacing it by its average over realization. So going from here to here is not exact. This would be only exact in the limit of n goes to infinity, but because there will be corrections here which are order of 1 over square root of n. And the way to see that that the corrections are order 1 over square root of n is to look at the variance of this term. So it's a sum of n variables, and its variance will go like 1 over n, or the standard, and the fluctuations will be 1 over square root of n. So this equation can be written explicitly. So let me write it explicitly. And then perhaps it will be clearer what I mean by this average over realizations. So M1 dot is equal to minus M1. This is this part. But what do I mean by averaging over realizations? So P1 can be plus or minus 1. P2 can be plus or minus 1. And P3 can be plus or minus 1. And each one is expected to appear with a probability 1 over 8. So I'm going to write down all the possibilities. So one possibility is that P1 is equal to 1, P2 is equal to 1, and P3 is equal to 1. So this would give us hyperbolic tangent of beta times, so I have 1 here because of P1 is equal to 1. Maybe I will explicitly write it. So we have 1 times hyperbolic tangent of beta times 1 times M1 plus 1 times M2 plus 1 times M3. So this is the first term. And I need more space, so I'm going just to delete this line and rewrite it. So no need to copy, okay? So M1 dot is equal to minus M1 plus 1 over 8, 1 times hyperbolic tangent of beta 1 times M1 plus 1 times M2 plus 1 times M3. So this is the first term. Second term would be, I'm going to take P3 to be minus 1. So second term would be plus 1 times hyperbolic tangent of beta 1 times M1 plus 1 times M2 minus 1 times M3. So this is the second term. This is a term in which P3 is minus 1 and P1 and P2 are plus 1. And I'll be quicker in writing the rest of them. So the third term would be P2 is equal to minus 1 and all the rest are plus 1. So this would be hyperbolic tangent of beta m1 minus m2 plus m3. Fourth term, I'm going to take p2 and p3 to be equal to -1. So this would be plus hyperbolic tangent of beta m1 minus m2 minus m3. And then I have 4 more terms in which p1 is equal to 1. Minus hyperbolic tangent of beta minus m1 plus m2 plus m3 minus hyperbolic tangent of beta minus m1 plus m2 minus m3 and the last two would be minus hyperbolic tangent of beta minus m1 minus m2 plus m3, and the last one would be minus hyperbolic tangent of beta minus m1 minus m2 minus m3. And this is the end. So this is the meaning of this average. So I'm taking all possible realizations of the different p's, each one with its probability, which in this case is 1/8. Questions? But if you look carefully, you see that actually there are things that repeat. What are the things that repeat? So this one is equal to this one. What else? This one is equal to this one. And this one should be equal to this one, and this one should be equal to this one. Okay? So it's easier. It's equal to minus m1 plus 1/4 hyperbolic tangent of beta m1 plus m2 plus m3 plus hyperbolic tangent of beta m1 plus m2 minus m3 plus hyperbolic tangent of beta m1 minus m2 plus m3 plus hyperbolic tangent of beta m1 minus m2 minus m3 Okay, so this is the equation for m1 dot. And next we'll have an equation for m2 dot. Which will be very similar. Wherever we have m1, wherever we have 1, we'll have to replace with 2. And there will be another equation for m3 dot. So in the previous case, we had one differential equation that we had to find the fixed point and study its stability. Now we have 3 differential equations for which we have to find fixed points and study stability. 3 is worse than 1, right? 1 is easier, but it is better than n. And there is some structure here. So how are we going to find the fixed points? It's not trivial because we have a set of 3 equations, 3 nonlinear equations. So what kind of fixed points do we expect? What do you mean by symmetric? I'm sorry? Okay. So there's symmetry in this set of equations, so we may expect a symmetric. So considering the symmetry, you say we should expect a symmetric solution, unless there's symmetry breaking. Okay, so that's. I mean, it's a valid consideration, and indeed we will look for a symmetric equation. But from what we know, so we know something about these equations. For example, we know that in the limit of beta going to infinity, what do we know about these equations? We know something about the fixed point of this, at least some of the fixed points of these equations, because we've already studied the case of large beta. So in the case of large beta, we showed that memory patterns are fixed points of the dynamics. So in the limit of large beta, we expect a solution in which the overlap with one of the memory patterns is large. So in the limit of a large beta, we expect a solution that we expect a fixed point solution of fm1 being close to 1. Or m2 is close to 1. But it's difficult to study these equations because even if we know that m1 is close to 1, we don't know anything about m2, right? Well, wrong. We know something about m2 if we know that m1 is close to 1. If m1 is close to 1, what does it mean? It means that the pattern of activity in the network is similar to one of the similar to memory pattern number 1. So if the pattern of activity is similar to memory pattern number 1, what can we say about the overlap with memory pattern number 2? It will be almost orthogonal. Because these are two stochastic, these are two, the product of the sum of the mean of a product of pluses and minus ones, and this should be equal to 0 up to corrections which are 1 over square root of n. So if m1 is equal to 1, then m2 and m3, or if m1 is close to 1, then m2 or m3 should be close to 0. So looking at these equations, well, this would become beta m1, and this would become beta m1, and this would become beta m1, and this would become beta m1, because m2 and m3 are very small. And we can do a similar thing for m2 dot and m3 dot, and then, well, we can even just looking at the first equation, then m1 is approximately equal to 1 over 4 of sum of 4 hyperbolic tangent beta m1, and this we've already solved in the case of p is equal to 1. So we expect a solution, at least when beta is large, we expect a solution which m1 is a solution of this equation, and m2 and m3 are equal to 0. And another fixed point solution which m2 is equal to hyperbolic tangent of beta m2, and in this case m1 and m3 will be equal to 0, and third fixed point, or a third pair of fixed points in which that solve the equation m3 star is equal to hyperbolic tangent of beta m3, and m2 and m1 are equal to 0. Let's take a break, and after the break we will continue with this equation.
הפאטרנס, אנחנו פיתחנו אותם שהם יהיו אורתוגונליים אחד לשני, או שהם אורתוגונליים בגלל שהם סטוכסטיים?
הם כמעט אורתוגונליים בגלל שהם סטוכסטיים. למעשה הם היו אורתוגונליים, זה היה יותר טוב, כי כל הרעש שדיברנו עליו כשחשבנו סיגנל טו נויז, הכל התחיל איברים של, הכנסת את פאטרן אחד, הסתכלת על האוברלאפ עם פאטרן 2, 3, 4, וסתכנת על כל הדברים. אז אם כל הפאטרנס היו באמת אורתוגונליים, אז לא היה לך רעש. רעש היה אפס. הפאטרנס הם כמעט אורתוגונליים. כשיש לך הרבה כאלה, זה נהיה בעיה. Okay, so we are talking about Hopfield model, beta, intermediate range of beta, when three memory patterns are embedded in the network. We wrote three equations. Well, we wrote one, but we know how to write the other two for the overlap with the three memory patterns. And we want to find the fixed points. And we had there were two suggestions or two points of view about how to find them. So one said, we know that in the limit of beta is infinite, we expect to find solutions with a large overlap with one of the memory patterns. And since the memory patterns are approximately orthogonal, then we expect to find a fixed point which have a high overlap with one of the memory patterns. This was one consideration. Another consideration said something different. Said there is symmetry in the equations. So let's look for a symmetric solution. And these two approaches would result in different fixed points, but these are the nonlinear equations, so it could be that these equations have many or at least several fixed points. So I will start with the first and then go to your suggestion. So I will start with considering the case. So we'll consider initial conditions. Initial conditions. So the vector of activity at time t is equal to 0 will be equal to something like this. So there will be some the first Q neurons, the activity of the first Q neurons will be equal to memory pattern number 1, and the rest will be equal to minus memory pattern number 1. So this would be the vector. Let's write it as a vector. So we're thinking about initial conditions in which we have partial overlap with memory pattern 1 and partial overlap with minus memory pattern 1. And as Musa noted previously, well, at least in the case of P is equal to 1, the case of one memory pattern, we expect that a memory pattern will be a fixed point in the limit of large beta, and minus a memory pattern will be a fixed point. And this we saw when solving this equation. So now we start with a case that some of the neurons are congruent with or equal to memory pattern number 1, and some are the opposite of memory pattern 1. And it's easy to show that Q, the number of neurons that are congruent with memory pattern 1, can be written using the overlap. So this will be equal to the initial overlap with memory pattern number 1 plus the overlap divided by 2 times n, and the 1 minus Q will be equal to 1 minus the overlap over 2 times n. So one way to think about it is if Q is equal to 1/2, then the overlap will be equal to 0, and then Q is n over 2. So if half of the neurons are equal to memory pattern 1 and half are equal to minus memory pattern 1, then Q is equal to n over 2, and the overlap is equal to 0. So how would these equations look like? And this is something we started discussing before the break. Now, if the memory patterns are orthogonal to one another, and also the minus memory patterns are orthogonal to one another. So if the initial condition is memory pattern number 1 and minus memory pattern number 1, then we expect that there will be a positive overlap with memory pattern number 1, unless Q is exactly equal to 1/2. But the overlap with all other memory patterns will be close to 0, because the memories are approximately orthogonal. So starting with these initial conditions, the dynamics will be dynamics of that will look something like this. So the dynamics would be m1 dot is equal to minus, be approximately equal to minus m1 plus hyperbolic tangent of beta m1, and m2 dot will be equal to minus m2, and m3 dot will be equal to minus m3, and then we will converge to a solution that is exactly the solution that we had in the case of one memory pattern, and this solution will be where we're thinking about beta that is larger than 1, that this solution will be stable, and it will be a solution with either positive overlap or negative overlap with memory pattern 1, depending on the initial conditions, and no overlap with the other two memory patterns. Questions about that? So we've already identified 6. If beta is larger than 1, we have identified 6 fixed points. 6 stable fixed points. What are the stable fixed points? M1 positive, and all other m's are 0. M1 is negative, all other m's are 0. M2 is positive, M2 is negative, M3 is positive, M3 is negative. So these are the three fixed points. But now we want to go back to your suggestion, which is to think about the symmetry in this problem. So what kind of symmetric solution can we envision here? So symmetric solution would be an equal overlap with all 3 memory patterns. But what kind of symmetric overlap can we have? For example, is it possible that M1 will be equal to 1, M2 will be equal to 1, and M3 will be equal to 1? Clearly not, right? Because, well, if M1 is equal to 1, then M2 has to be equal to 0. So what will be what kind of symmetric solution can we expect? So I'm going to consider the following initial condition. So the initial condition that I'm going to consider is that the activity of neuron I at time t is equal to 0 is given by the majority rule on the memory patterns. So we have 3 memory patterns, 1, 2, and 3. And the initial condition that I'm going to consider is the activity of neuron I is equal to 1 if 2 or more of the memory patterns are +1 and equal to -1 otherwise. So what's the probability? What's the probability that the activity of neuron? What is the probability that the activity of neuron I at time t equal to 0 is equal to pi1? Or let's do the complementary calculation. What's the probability that the activity of a neuron will not be equal to 1, to the pattern of neuron 1? Well, in order for the initial condition to be different from memory pattern 1, what we need is that memory pattern 2 and memory pattern 3 will have the opposite sign. What's the probability that both of them will have the opposite sign? The probability that one of them will have the opposite sign is 1/2. So the probability that both of them will have the opposite sign is 1/4. So what will be M1 in this case? So in three quarter of the cases, the contribution would be 1. 1/4 of the cases, the contribution would be -1. So the average would be 1/2. So M1 is expected to be equal to 1/2. And M2, same as M1. So M1 will be equal to M2 at time t is equal to 0. So the overlap in this case with all three memory patterns will be 1/2. This is the initial condition. Actually, this is the highest overlap, highest symmetric overlap possible. So now we can go back to our differential equations and consider the stability. Oh, I'm sorry, consider and assume that we start with these initial conditions and see what's the fixed point. So thinking about M1, so assuming a symmetric solution, M1 is equal to M2 is equal to M3, the fixed point solution would be M is equal to 1/4 times hyperbolic tangent so here we will have 3 beta M and here we will have plus this would be the contribution of this term what about this one? So here we'll have again M1 M and here we'll have minus M. So this will cancel with this one. So now we have a new fixed point equation. And we can ask ourselves what would be the fixed point. So let's just denote it as a fixed point solution. So in the limit of beta going to infinity, this will be equal to sine of m, and this will be equal to sine of m. So in the limit of beta going to infinity, the equation will be m star is equal to 1/4 times 2 times sine of m star, or m star is equal to plus minus 1/2, which makes sense, right? This would correspond to the initial condition that we discussed. Okay. What about the case in which beta goes to 0? What will be the fixed point solution? So the fixed point solution will be simply m star is equal to 0. So at somewhere there should be a bifurcation going from 0 to 1/2. Solution be changing between 0 and 1/2. Where will this bifurcation point take place? How are we going to find it? How did we find the bifurcation point previously? We looked at the slope. Where? The slope where? At the fixed point. Which fixed point? Okay, so what will be the slope? What will be the slope at the fixed point? It's a 0 fixed point. So we're doing the same trick as before. We're looking at, so the homogeneous, one fixed point is m is equal to 0. And so we're looking at the slope of this function at 0. And what is the slope? It will be 1/4 times 3 beta plus beta. So the slope is beta, as before. So the bifurcation point will occur at exactly the same point. So from this analysis, we expect that for any value of beta such that we have a solution of one overlap of significant overlap with one of the memory patterns, there will also be a solution of an overlap with all 3 patterns, as you suggested. Questions? Is it clear what I'm doing? So a homogeneous fixed point exists, a fixed point in which all overlaps are equal, exists for a beta that is larger than 1 and does not exist for beta that is smaller than 1, as before. But the stability, now we can go back to the stability analysis, this is more challenging. So how are we going to study the stability of this homogeneous fixed point? So what do we need to compute? What matrix do we need to compute in order to analyze the stability of this homogeneous fixed point? So the matrix that we need to consider will have the form dmi dot dmj at this point of m1 is equal to m2 is equal to m3 is equal to m star. So this is a stability matrix that we need to analyze. Right? Questions? You're very quiet. So this matrix is a 3x3 matrix. So in principle, we need to compute 9 entries. But we can use symmetry in order to make our lives simpler. How are we going to do that? So we expect that dm2 dot dm2 will be equal to dm1 dot dm1 or dm3 dot dm3. We also expect that dm1 dot dm2 will be equal to dm1 dot dm3 or dm2 dot dm1 or dm2 dot dm3 and so on. So in fact, we only need to compute two terms. We need to compute dm1 dot dm1. This will give us a diagonal of the matrix. And we will need to compute dm1 dot dm2, and this will give us all the off-diagonal elements of the stability matrix. So let's look at dm1 dot dm1. This is equal to -1 from this term plus what? So we will have whenever we take the derivative, there will be a beta. So we have a beta over 4. So the derivative of hyperbolic tangent of x is 1 minus hyperbolic tangent square of x. So this will give us one minus hyperbolic tangent square of beta 3m. So this will be 3 beta m. So this is the derivative of this term. The derivative of this term will be also 1 minus hyperbolic tangent square. This will be also 1 minus hyperbolic tangent square, and this will also give us 1 minus hyperbolic tangent square, but different hyperbolic tangent squares. So each one of these will contribute 1. So we can replace this 1 by 4. So this will give us hyperbolic tangent square of 3m. This will give us hyperbolic tangent square of 1m, because m1 plus m2 minus m3. This will also give us 1m, and this will also give us 1m. M star, yeah, it's a fixed point, sure. Okay, now we need to compute dm1 dot dm2. So this will not contribute anything. This 3? Ah, because I made a mistake. Sorry. Is it better? Okay, so now we need to compute dm1 dot dm2. So let's see. We have 1 over 4, as always, and we have the beta. So this will be equal to beta over 4. So here, this will give us 1 minus hyperbolic tangent square. This will also give us 1 minus hyperbolic tangent square. This will give us minus 1 minus hyperbolic tangent square because of the minus here. And this will also give us minus 1 minus hyperbolic tangent square. So this will give us 1 and 1. This will give us minus 1, minus 1. So we don't have a contribution of a term that is not that doesn't have a hyperbolic tangent square. So now we need to look at the actual value. So here we'll have hyperbolic tangent square of 3m. I can write it. Okay. So we are done with this term, and now we have this one. This one will be, as before, hyperbolic tangent square of m, beta m. This will give us minus hyperbolic tangent square because of the minus here, and this will give us minus hyperbolic tangent square. So this would be minus hyperbolic tangent square of beta m. So I'm going to denote this by A and denote this by B. And the stability matrix will have the form of A, B, 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 A, B, 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 A. So now we need to find the eigenvalues of this matrix. Now this is ugly and complicated, and we don't enjoy hard work. So let's consider limits. Let's start by considering different limits. So let's start with a limit of beta going to infinity. So let's look at this term. So here we have 4 minus in the limit of beta going to infinity. What will this be equal to? 1, and this also 1. Well, 3. So we have 4 minus 3, 1 minus 1 minus 3, which is equal to 0, times beta, which is equal to infinite. This is infinity times 0. So what can we say about this term? Well, it turns out, and I leave it to you as an exercise to prove, that in the limit of beta, that beta goes to infinity, this product goes to 0. The reason is that hyperbolic tangent has an exponent in it, so this becomes closer to 1 faster than this one grows. That's the reason. So the limit of in the limit of beta going to infinity, A is equal to minus 1. In the limit of beta going to infinity, B is equal to what? Well, this will be equal to 1. This will be equal to 1. 1 minus 1 is 0. 0 times beta, 0 times infinity, but using the same argument and in exactly the same way, one can prove that in this limit beta will be equal to 0. So the stability matrix will become minus 1, minus 1, minus 1, a diagonal matrix, and the fixed point is stable. So going back to thinking about memories, what we've just proven is that in the case of 3 memory patterns, it's not only that each memory and its minus are stable fixed points of the dynamics, also each combination or a combination of 3 memory patterns is also a stable fixed point of the dynamics. And how many such combinations do we have? So we considered in this case a case where M1 is equal to M2 is equal to M3. But we could have done exactly the same analysis for the case of M1 is equal to M2 is equal to minus M3. Or M1 is equal to minus M2 is equal to M3. Or, well, all 8 combinations. So with these 3 memory patterns, in fact, the number of fixed points is much larger well, it's not much larger, it's larger than we thought. It's not only that the memory patterns are fixed points of the dynamics, also a combination, a symmetric combination of all the memory patterns is also, or all the symmetric combinations of memory patterns and minus memory patterns are also fixed points of the dynamics. Now it turns out that if we add more memories, this is a network with only 3 memories, you could consider a case, what about a case of 5 memory patterns, if we embed 5 memory patterns in the network? So we already know that all 5 memory patterns and minus memory patterns will be fixed points. How many such fixed points will we have? Maybe 10. So all memory patterns and their minuses. But also all symmetric combinations of 5 will also be fixed points. How many such combinations do we have? 2 to the 5. In addition, we'll have all combinations of 3. And if we have a network with 7, that we embed 7 memory patterns, well, we have all symmetric combinations of the 7, 2 to the 7 such combinations, all symmetric combinations of the 5, and all symmetric combinations of the 3. So in fact, in the limit of beta going to infinity that we studied, we have many, many more stable fixed points than we initially guessed. Initially, we just asked the question, okay, will a memory pattern be a fixed point? But we didn't ask the question, okay, what about other fixed points? Turns out that there are many more fixed points which are not memory patterns, which are combinations of memory patterns than these memory patterns. In fact, in the limit of large P, the number of fixed points of the dynamics becomes exponential. If this would be, and the dynamics becomes similar to the dynamics of spin glasses in physics. Before talking about other limits when not the limit of beta going to infinity, I would like to comment about the biological plausibility of these memories. So one possibility is to argue one possibility is to argue that this is a bug of the model, and in fact we will show that when beta, for smaller values of beta, these other fixed points become unstable, while the memory patterns are stable. That's one way of thinking about it. But another way of thinking about it is that these combined memory patterns generate hierarchies of memories. So you can think about memories of, I don't know, animals. So I have dog, a cat, and together they are both pets, or mammals. So you can think about hierarchies of memories that combine several memories together. So these memories that have positive overlap with several memory patterns can be thought of as a superclass of memories. And actually, there is from a computational point of view, it's worthwhile having these memories. Questions? Okay. So now we are going to study the stability of this matrix, not in this limit, but in a more general case. So the first step would be to identify or guess the eigenvalues of this matrix given these A's and B's. So what will be the eigenvalues and eigenvectors of this matrix? So let's think about it from the perspective of symmetry. So the problem has symmetry in it. We're considering a solution that has symmetry in it. So what kind of symmetric perturbation can you think about? So at the fixed point, M1 is equal to M2 is equal to M3 is equal to some M star. What kind of perturbation can you think about that preserves this symmetry? This is a perturbation in the direction of 1, 1, 1, in the homogeneous direction. Perturbation in which all three change together. And the corresponding eigenvector will be the homogeneous eigenvector. So one eigenvector to consider, let's call it U homogeneous, will be 1, 1, 1. And what will be the corresponding eigenvalue? So what will be the homogeneous eigenvalue, the eigenvalue that corresponds to this eigenvector? I'm sorry? So this would be simply A plus 2B. Okay. What other eigenvalues and eigenvectors do? What other eigenvectors do we expect to see here? Again, looking at the symmetry of the matrix or symmetry of the equations. So this homogeneous eigenvector corresponds to a perturbation in which all three change together. Other eigenvectors will have to be orthogonal to this homogeneous direction. So we can think about, for example, this eigenvector or this eigenvector. And it's easy to see that both of them are eigenvectors. Any combination of these will also be an eigenvector. So this was an eigenvector. This is a direction in which one is going up, one is going down, and the other one is not changing. This is the second eigenvector. And the corresponding eigenvalue will be A minus B. So we would be interested in computing the values of these eigenvalues for beta that is not infinite. Well, beta that is equal to 0 is not very interesting. Why is that? This is a 0 fixed point that we discussed previously. Would be the case of a single 0 fixed point. We'd be interested in computing these eigenvalues for beta that is between smaller than infinite and larger than 1. So the limit of beta going to infinity, this is something that was easy to do. And what we would like to do now is compute it in the limit of beta that is, we will do it for beta that is slightly larger than 1. Why is it an easy limit, or relatively easy limit? We can tailor expand the fixed point equations. We can tailor expand the fixed point equations to find m as a function of beta. And then we can tailor expand these equations around this perturbed solution. And this is something that we will do on Thursday. So we'll use Taylor expansion, Taylor series to find the fixed point solution, where the small parameter is beta minus 1. And we will Taylor expand this solution around 0, around this solution, again with a small parameter being beta minus 1. And then we will be able to compute the values of the homogeneous and heterogeneous eigenvalues in this limit where beta is close to 1, slightly larger than 1. Questions? Okay. אנשים אחרים יגידו לך דברים אחרים. אין פה איזה אמת מיוחד. נגיד, יש מקומות שבהם אתה חייב לעשות 3 מעבדות.